Okay, number 70. This is part 2. Okay, part 2 of 6.6 and 6.7. Part 2. For f of x, which is e to the x, describe how each transformation affects the domain, range, asymptotes, and y-intercept. So y equals e to the x is basically this one. Y is e to the x. Its domain is all real numbers, right? So it's from negative infinity to infinity. And its range is all positive real numbers. So it does not include 0, so you have to have a parenthesis here, 0, comma, infinity. And its asymptote is just x-axis, so its y is equal to 0, and its y-intercept is this one at 1, so that's 0, comma 1. So how do they affect, these transformations affect the domain, range, asymptote, and y-intercept? Okay, A, vertical stretch. So if you do a vertical stretch on this one, for example, y is equal to 2 to the power of 2 times e to the power of x, then when you vertically stretch it, as we've seen in part 1, the asymptote does not change. It just becomes something like this. It rises faster and goes down faster, like this. No, sorry, it's a vertical stretch, so it's not this. Sorry about that. Vertical stretch means, oops, it's not this one. Okay, let me erase this thing. Okay. So it's going to be stretched upward like this. Okay. Now instead of 1, it's going to pass through 2. All right. So even though you do that, its domain still remains the same. The range also remains the same. Okay. Why? I mean, this end will keep decreasing and eventually gets closer to the x-axis. So it's from 0 to infinity. B, horizontal stretch. If you stretch it horizontally, it gets stretched like this way. Then its domain still remains the same, range remains the same. Vertical translation. Vertical translation means you shift this black graph upward without changing the shape of it. So when you translate it, the asymptote gets translated too, okay? So asymptote changes, domain still remains the same. The range is not going to go from 0 to infinity, but if you translate it 2 units upward, for example, then range is what? Is from 2 to infinity then, okay? And asymptote becomes y is equal to 2. Y-intercept also changes, okay? If you shift it 2 upward, okay, this one becomes 0, comma 3. So you add 2 to it. In a vertical stretch, there's one thing that changes, y-intercept, okay? As I said, it was passing through 1, but it now passes through 2 if you have something like this. So y-intercept changes in all cases, A and C, okay? Horizontal stretch, it can also change. Horizontal translation, it also changes because this one shifts to the right or left. So if you do that, obviously, y-intercept changes. But domain does not change, range does not change, asymptote does not change. So the only thing that changes in horizontal translation would be the y-intercept. Okay. Try to do 71 by yourself. Okay. Let me go over to the next one. The amount of radioactive strontium-90 remaining after t years decreases according to the function nt is equal to n naught times e to the negative 0.0238 t. How much of a 40-gram sample will remain after 25 years? Remember, for continuous growth or decay, we were given this formula. The final amount A would be A0, okay, the initial amount, times e to the power of RT. R is the growth rate or decay rate, okay? So it says negative 0.0238 t as an exponent. So that means it's a negative growth. So it's a decay, okay? So it says decreases, okay? The radioactive strontium-90, okay, decreases according to this function. So you just plug in the numbers here. How much of a 40-gram sample will remain after 25 years? So this is the initial amount. So N0 in this case is 40 grams. That's 40. After 25 years, so T is equal to 25. So plug this number in here. So basically what you're finding is N25. So N0 is 40 times e to the power of negative 0.0238 times 25. So you need a calculator for this. So where's my calculator? Okay. So that's 40 times e to the power of negative 0.0238 times 25. So you get 22.0625. You have other numbers after this, but I'll just stop right there. Okay? So you'll have 22.0625 grams remaining after 25 years. So it's a simple matter of plugging in the numbers, so it's very easy. So let me just skip over to the next one. 74. Compare the growth of an investment of $2,000 in two different accounts. One account earns 30% annual interest, the other earns 5% annual interest, and both are compounded continuously over 20 years. Okay, so both are continuous compounding. Okay? So T, in this case, is 20 years, so 20. For the first one, it earns 3% interest, so R is 0.03. And for the second one, R is 0.05. The initial investment is 2,000. So I'm going to use A is equal to, so I said A part, okay? A is equal to P times the principal times e to the RT power. So we're comparing two, okay? One at 3% and one at 5%. Let's compare these two. So for 3%, account balance after 20 years would be A is equal to P, which is 2,000 times E. Okay, let me erase that parenthesis here. Times e to the power of 0.03, the rate, times t, which is 20. So this is 2,000 times e to the power of 0.0, oops, to the power of 0.03 times 20. That's $3,644.24. Okay, the account balance after 20 years for account earning 5% interest is 2,000 times e to the power of 0.05 times 20. Okay, 2,000 times e to the power of 0.05 times 20. So you'll get 5,436.56. So it's just a 2% difference in interest rate, and the ending balance, okay, after 20 years has a huge difference, okay? One at 3,600, one at like 5,400. So there's a difference of like what, $1,800 almost, okay? All right, next one, archaeology. A wooden chest is found and is said to be from the 2nd century BCE. Tests on a sample of wood from the chest reveal that it contains 92% of its original carbon-14. Could the chest be from the 2nd century BCE? In order for us to find out the answer for this, we need to have a the half-life for carbon-14. Okay, let me look up half-life for carbon-14. It's 5,000 some number of years. Let me see. The textbook gave you that number, but I don't remember exactly how long that was. It's like 5,840 or something. Let me double check. Okay, let me see. I just opened up the book. All right. I can simply look it up on the internet, but I want to use a number that's specifically given in the book. Let me see. Where was it? It's 5730. 5730. So half-life of carbon-14 is 5730 years. Okay, if you know the half-life of carbon-14, what you can do is you can calculate the rate of decay from this information. So how do you do that? You use this formula, A part. Let's say you start from the initial amount is P. Half-life means that exactly half of this initial amount remains in 5,730 years. So the final amount would be P over 2. It's a half of that. So you plug in p over 2 into this a, and the initial is p, or you can just say this is 1 and this decreases to 1/2. Then it gets simpler than this, okay? So e to the r times t is what? 5730 times 5730. You can set it up this way, or you can cancel out p, or plug in 1 and 1 over 2 for initial and final. So that's 1 over 2 is equal to 1 times e to the power of r times 5730. Either way is just fine. You eventually come to the same conclusion here. So anyway, so this one says e to the power of 5730r is equal to 1/2. In order to find out this r, you need to apply natural log on both sides. So ln okay, ln e to the power of 5730r is equal to ln 1 over 2. Using property of logs, you can bring this number or this expression in front of this ln. Then this becomes, let me come over here, 5730r ln e is equal to ln 1 over 2. And we know that this ln e is just 1, okay? So basically what you have is 5730r is equal to ln 1 over 2. So r will be ln 1 over 2 divided by 5730. So if you put this into your calculator, okay, ln 1/2 divided by 5730, you get this number, negative 1.20968094 times 10 to the power of negative 4. Now you can complete this expression with the what? Decay rate. So finally, we arrive at this. A is P times E to the power of negative 1.20968094 times 10 to the negative 4th, okay, times T. Okay, this one says now it contains 92% of its original carbon-14 after some number of years T. So if the initial amount was 100%, if this is 100%, which is 1, 92% of its original remains here. So A is 0.92. So plug those numbers to these A and P, and you can find out this T to approximate the number of years that has passed since the original carbon-14 sample was started decaying, okay? Okay, so 0.92 is equal to e to the power of negative 1.20968094 times 10 to the negative 4th times t. Now you can apply natural log. Ln 0.92 is equal to ln e to the power of negative 1.20968094 times 10 to the negative 4th times t. And then you can bring this expression in front of this log. Okay? Then this becomes, let me switch right hand side and left hand side. So that becomes negative 1.20968094 0.20968094 times 10 to the negative fourth times t. And ln E is 1, so you don't have to write that down. And this is equal to ln 0.92. So t is equal to ln 0.92 divided by negative 1.20968094 times 10 to the negative fourth. So put that into your calculator and you'll see that, okay, ln 0.92 divided by negative 1.20968094 part of negative 4. Then this is 689.2. I'll just round it to the hundredth, 29 years. So you know that this sample is from 689 years ago, okay? So could the chest be from the 2nd century BCE? Absolutely no, okay? 2nd century means it's like, what? BCE 100 something years. So we're in like 2024 right now, so 600 or 700 years ago is not obviously what? 100 some number of years, okay? So the answer is no. Okay, let's now look at this one. Assume that all interest rates are compounded continuously. So you can use A is equal to P times e to the RT for all of these. How long will it take an investment of $5,000 to double if the annual interest rate is 6%? So for 77, investment doubles from 5,000. Then the final amount would be double of that, which is 10,000 is equal to 5,000 times e to the rate is 6%, so that's r is equal to 0.06. That's 0.06t. So divide each side by 5,000, so you get 2 is equal to e to the power of 0.06t. So apply ln on both sides, so ln e to the 0.06t is equal to ln 2. So take this number, the exponent, in front of the log. So you get 0.06t. ln e is 1, so it disappears. It's equal to ln 2. So t is equal to ln 2 divided by 0.06. So I'll put it into the calculator. ln 2 divided by 0.06. So that's 11.55. So it takes about 11 and a half years for your investment to double, okay? At 6%. 78, how long will it take an investment to double at 10% annual interest rate? So same thing, okay? The only difference is the what? Difference in rates, okay? From 6% to 10%. So I'm going to take this one and I'll put in what? The rate r of 0.1. So this becomes e to the power of 0.1t, and this should equal 2. So apply ln on both sides, then ln e to the power of 0.1t is equal to ln 2. So 0.1t, so take this thing in front of this log, and ln e is 1, so it disappears. That's ln 2. So t is equal to ln 2 divided by 0.1. I'll do the same thing here. ln2 divided by 0.06. Oh, no, 0.1, sorry, 0.1. 6.93. So this means when interest rate increases from 6% to 10%, the doubling time for your investment gets reduced to what? 11.5 years to 6.93 years, almost like 7 years. Okay? 79, if it takes a certain amount of money, 3.7 years to double, at what annual interest rate was the money invested? So for 79, so investment doubled. So if you started with 1, it doubled. So the final amount is 2. So 2 is equal to 1 times e to the power of, we don't know the rate, r t. T is like 3.7 years. So let me rewrite that. 3.7 r. Let me apply a natural log on both sides. So ln a to the 3.7 r is equal to ln 2. Take this and bring it over here. So 3.7 r times ln e. Ln e is 1, so I'm not going to write that. It's equal to ln 2. So r is ln 2 over 3.7. Okay, so ln 2 divided by 3.7 is 0.187337 approximately. There are other numbers after this, but I'll just cut it off here. So R is 0.187337, meaning the interest rate is 18.7337%. Okay. So interest rate is higher than all of these. So doubling time is very short, 3.7 years. Okay. Next one. Solve each equation for x. Write the exact solution and the approximate solutions to the nearest hundredth when appropriate. And for something like 8, it's very easy. I mean, obviously x must be 4 for them to be equal to each other, okay? These are very easy, so let me jump over to 15 maybe, 15. So 15, e to the 2x is equal to 20. So to find out x, which is in the exponent, you need log. Whenever there's a variable in the exponent, you need to use log, okay? So base is e, so I'm going to use natural log. ln e to the 2x is equal to ln 20. So apply natural log on both sides. So that means 2x, ln e is 1, so that's 1. So it's simply 2x. 2x is equal to ln 20. So x is ln 20 over 2. So you need to use your calculator here. ln 20 divided by 2 is 1.4978, but we're rounding to the nearest hundredth. So that's 1.50. All right, we can do the same thing for 16. 17, obviously easy. Let me do something like 21. Okay. 3 ln x is equal to ln 4 plus ln 2. Okay, if you have multiple logs, like on the right hand side, just combine them together. It's got the same base e here, so you can combine these two logs together, and at the same time, take this number and take it back here as an exponent. So ln x cubed is ln 4 times 2, right? So that's ln 8. Now what you have is natural log on the left hand side and natural log on the right hand side. So cancel these ln's from each side. So you end up with x cubed is equal to 8. So x is 2. Easy. We've done something like these in the previous sections on not natural log but using logs with other bases. So same thing, there are same logs, same principles apply here. So it's a repetition of the kind of problems that we've done before. So this should be not hard but easy. Okay, that's 25. All right, what am I gonna do with this? I'm gonna say, okay, I'll take this thing back here. So log x cubed is equal to, take this thing and, okay, move it to the other side. So this is negative 2. So what does this mean? That's a common log. So its base is 10. So this means 10 to the power of this negative 2 will give you x cubed. So x cubed is equal to 10 to the power of negative 2. So what's x? So you can apply this power of 1 over 3 on both sides. Then multiply these two together, you end up with x. So x is what? This is multiply these two together, 10 to the power of negative 2 over 3. So that's going to be your answer, okay? You can do the rest of the stuff by yourself. Okay, next one, demographics. The population of India was estimated to be 574,220,000 in 1974 and 746,388,000 in 1984. Assume that this population growth is exponential. Let t is equal to 0 represent 1974 and t is equal to 10 represents 1984. Use the exponential growth function, okay, pt is equal to p naught times e to the kt to find the value of k. Then write the function for this population as a function of time t. All right, so we started with this much population, this many population. So that's p0. And this is p after how many years? 10 years. T is equal to 10. So for A, you can plug in 574,220,000 into P0, and this one times E to the power of K times T. T is 10, so 10K is equal to this number, 746,388,000. So e to the power of 10k is equal to this thing, 746 million over 574 million. So let me calculate that here. That's 2998 29334. And you can apply ln on both sides. So this becomes 10k. ln e is 1, so disappears, is equal to ln 1.299829334. So k, so cancel this one and divide this thing by 10. So this is ln this thing divided by 10 is 0.026 223 2974. Okay, so the function for this population is a function of time t. So we can say that pt is equal to p0 times e to the power of 0.026 223 2974 t. Okay. And this p0 is, as you can see, that's 574,220,000. Okay. B, estimate the population in 2004 rounded to the nearest 100,000. So for B, so 2004 is how many years after 1974? That's what? 30 years later. So you're looking for P30, okay? So 574, the initial population, 574,220,000 times e to the power of 0.026 223 2974 times 30 is equal to e to the power of answer times 30 is, wow, it's this number. Comma, comma, comma. So that's 1,261,064,544 people. C, use the function you wrote in part A to estimate the year in which the population will reach 1.5 billion. So you put 1.5 here. 1.5 billion is this much. And you still have this much for the right hand side. E to the power of this much, 0.02622329774t. And you're looking for this t. So divide, okay, cancel this one. Divide this number by that number, 574 million. And this becomes 1500000. The last three zeros or 4 zeros are not needed. So it's 2.6. So e to the power of 0.026 0.26223297 is equal to 2.612239,211. So here you can apply natural log on both sides like this. Then this expression can come in front of ln. ln e is 1 again. So you end up with 0.02622323234 t is equal to ln 2.612239,211. So you divide each side by this number. So you divide this thing by 0.02622323974. So t is equal to calculator time ln answer divided by 0.02622323974. So you get 36.62, approximately this much. So it takes about 36.62 years, okay, for the population of India to reach 1.5 billion. Okay. All right, that's it. That's the end of part 2.